welcome once again friends to this NPTEL module on handling large scale unit level data using Stata. We have already discussed the very basics of regression analysis, the linear regression analysis in the previous lecture with their very important properties related to population trend line and the sample out of it and their statistics. Now, we are going to discuss some further details related to the linear regression analysis. Now, to start with the linear regression analysis, most important technique is through ordinary least square method. Ordinary least square method, there are important interpretations to it. We need to discuss about the least square approach of the error term. Why least square? Because just averaging the square of the error term I think I have already shown you. If we simply take the error term which are deviating from the standard trend line, if there are so many errors, positive and negative errors are there from the trend line, if I simply take an average, average might be 0, okay. But if the average is 0, that cannot guarantee the estimation. I mean basically average might be 0, but if you square the error term, the minimum most error term if it is attached, then we can able to estimate correctly. Okay. The error term, by squaring the error term, instead of just taking the average, if that gets to 0, we cannot able to estimate anything, because it has already converted to a 0 value, we cannot derive the equation for estimation. But by squaring the errors, it is not going to be 0, okay. Every time the error term we are going to square, that means a positive value will be boiled down. So, error term whatever is there, we are actually converting that to a positive value. So, positive value if it is minimized, then that is actually called the best method to estimate, and that once the model ensures that you have reached into a minimum most square of the error terms, you can able to estimate the best coefficient out of it. That is why it is called the ordinary least square method. Now, this is also abbreviated with OLS in simple language. Then most commonly used method to obtain some reasonably good estimate of betas, which help the most in studying y as affected by x. So, in our example or in our previous equation, we mentioned that we are supposed to derive the estimated value of it, that is in terms of beta naught head and beta 1 head. Okay. We are referring to the estimated value and are obtained by finding the values of beta naught head and beta 1 head that minimize the sum of square differences between y and y hat. Okay. Y hat basically the basically the estimated value. So, this is nothing but the error term. Okay. So, this is the y hat that gets defined with the help of beta naught, the intercept coefficient as well as the slope coefficient. Okay. Now, sum of the error term. Now, why I said error term has to be sum of the error term, if it is 0, minimizing to it. If it is near about 0, then we can able to estimate and this is the equation which I already said. Okay. Sum of the error term, now the squaring of the error, basically yi minus beta naught plus beta 1 xy is equal to this. Now, this is sum of error is also called as sum of squares, error sum of square. This is also called error sum of squares. Okay. We are going to discuss what is this ESS and how this is going to be useful for understanding the best fit of that trend line. Okay. The sum is taken over all the observations and their points are actually taken. The interpretation of the slope and intercept is also important. Now, this is the slope, the intercept of the coefficient of the intercept, and this is the coefficient of the slope. And beta naught is the estimated, every time I am mentioning hat, if you are mentioning that indicates estimated average value of y given the value of x when it is equal to 0. Okay, that means when x is 0, when it is I told you already beta naught refers to autonomous variable. Okay, it is all intercept term. So, autonomous means it is not affected by change of 0 change of value of x. So, therefore, when there is a 0 change in x, what is the impact of impact on y? Okay, that is nothing but called beta naught hat. So, beta 1 hat is the estimated change in the average value of y as a result of 1 unit of change of x, that we already mentioned in earlier slides or in our earlier lecture also. Now, coming to the graphical interpretation of the least square method, why least square is important. So, the average like in this case the model, if you take the least square, that means we can able to estimate the best fit line, but if you do not take square of it, it could be also negative. Okay. The average of the error could be negative or could be positive, but if it is negative, then actually the trend line is explaining nothing. Okay. So, nowhere it is saying it is within the space of x and y. Okay. So, the error term has to be squared. Now, this is first error term at this particular point. There are numerous error term possible, but if I writing down error term error hat 1, error hat 2, 3, 4 like this. Okay. Least square means sum of EI square. Okay. So, and so on. In this case 4 are there. So, we are writing 4. Now, what are the coefficient equations? We have predicted equations like predicted equations that is beta naught hat and beta 1 hat xi. The sample slope based on these predicted equation is that the beta 1, how beta 1 is defined, that is basically derived from the square of the error term, which we already mentioned a couple of minutes back in this equation. Okay. So, beta 1 can be derived from that basically that is called the sum of xi x bar minus yi y bar, sum of square between xy and divided by sum of square between the independent variables. Okay. So, sum of square, that is basically this is called the variance term, this is called covariance term. Okay. Covariance term and this is called variance term. So, variance. So, covariance basically the relations between two, that is dependent variable independent variable with respect to the total variable variance of the independent variable. Okay. So, what is the basically what is the unit change of the variance of the independent variable on the relationship between the two variables. Okay. So, that is the beauty of beta 1 hat. Okay, that really explains the change in the nature of x and y. Okay. Now, coming to the y intercept, sample y intercept where that is basically indicated with beta naught hat, that simply when we take the average of it, since average of it, then this only boils down to be mean of x bar, because this is going to be constant. Okay. So, beta times number of beta we have, number of beta 1 we have, that will be simply averaged. Okay. So, y average minus x bar average with multiplied with its beta coefficient is going to estimate our intercept. Okay. So, that we will explain. I am not going to explain everything about the details of blue properties or other detailed properties, because this is going to be the explanation in econometric class, and I think any standard econometrics book, if you unfold and go by the pages that explain the blue properties. Okay, based linear unbiased estimator, why when beta naught has to be unbiased, why beta 1 has to be unbiased. Okay. So, that explanation you should follow on your own, we are not explaining. In fact, I am giving very important concept in this lecture. Next class we will have an applied version of all those coefficients and its estimated value. Now, coming to the most interesting part of our lecture is understanding the variation. So, now the beta estimated beta value gives the relationship between the variance relations between x and y with respect to the total variance of x. How the unit variance of x lead to the relationship variance between x and y. Okay, that is all about understanding the variance. But now the variation where the variance has a role has to be very clearly emphasized. When we are saying variance, somewhere we are also addressing the variation. Okay. The variation is explained by the error term, largely by the error term, but how, what is that variation? So, the total variation is composed of two parts. So, let us decompose that, the total variation. One is in terms of residual sum of square and another is called explained sum of square. Okay. So, TSS stands for total sum of square. Now, it is very interesting to understand. Look at this first, then you come back this. Okay. So, you look at this, what we try to explain is the following. Okay. So, the total, suppose this is a point, we are estimating the value is somewhere here. Okay. Now, what is the TSS in this case? Given a particular point, what is the TSS for our understanding? The TSS basically the yi, the particular point which we are referring here, corresponding to the xi value, that is xi. Okay. Now, in this case our total variance will be over, how to know the total variance? If you have a standard average of that distribution of the yi dependent variable. So, the average, if it is indicated here, this is actually the y bar line. Okay. So, when we know the average value it is projected or pointed out is constant throughout the x because it is average. Okay. So, the total change of the individual y is explained by this point. Okay. This is the total change, is not it? So, this is basically yi minus y bar and that is the total change given the xi, alright. But how to explain that the yi is deviating from its average value, it is corresponded by the xi variable. How to know it? If you can bifurcate, if you can decompose in terms of x, you can able to estimate the exact changes through x. Now, to do so, we have to take the help of estimated values. Okay. What is that? Estimated values means the estimated parameter, estimated line. Okay. The estimated line is explained by y hat. Okay. Y hat that is basically beta naught plus beta 1 x, okay, xi, okay, or beta naught hat plus beta 1 hat. Okay. Beta naught hat we have already explained number of times. So, this is xi. So, that yi hat once I estimated. So, this is now we can have a point here like here we have a point. From this point, this is basically the estimated difference. Okay. yi over the estimated value, yi over the estimated value, that's called the residual sum of square. Okay. So, how the individual y point is deviating from the estimated value. What are the vertical difference? We said several times these difference, if any important points are there, any points is here, any point is there, basically this is from the trend line, from the estimated value. So, the error or the epsilon, these are called epsilons. Okay. The epsilon and its square is actually measuring the RSS. Okay. So, yi minus yi hat and its square and its sum of square is going to give us the value. Okay. Now, if I only take, okay, instead of square, now we can get it clarified. If I only take without square, if square is not there, then that may boil down to 0 and whole equation may boil down to 0, it is not going to give any estimate value. So, square actually minimizes the error value, and the best minimum error if you can do, that is actually going to give a best unbiased estimator. Okay. So, blue property is somewhere validating our coefficients, where we can get it clarified. I am not spending more time on it. Now, what is also important, this part is explained by the error term. Okay. So, error sum of square or the residual sum of square we have explained. What about other part? This portion is actually called explained sum of square. Expand sum square means what? This we know that this is called from these to this, these to this. These to this is called this is our difference between y bar. Okay. This is total yi hat, this is totally yi hat minus y bar. Okay. Yi hat minus y bar, the gap is called estimated value, estimated sum of square. Okay. So, we are going to explain all those things in detail. I think my the slides has tried to explain these things in detail. You can go through and clarify it accordingly. Okay. Let us come to the goodness of fit. Goodness of fit is very important in regression analysis throughout, not just in this lecture, in other subsequent lectures you will be very careful enough to understand that goodness of fit. Basically, we are referring to the trend line every time. If your trend line is perfectly fit to the data or to the variation, if that is the variation is very close, that means our fit is, it has a very good goodness of fit, or our fit is very good. Okay. So, goodness of fit of a statistical model describes how well the model fit to its observations or data. Okay. It is used for model testing also, and especially for the panel data and for the time series data, they are very careful enough about this value. Okay. Sometimes for individual cross sectional data, they do not check it in detail, but we will discuss later on. But I just wanted to mention that the degree of agreement is a measure of the goodness of fit between data and model. The model is basically the fit and the data are the points. Okay. So, if the degree of agreement is good, then we have a better estimate. In regression analysis, coefficient of determination is considered as the goodness of fit of the model. So, coefficient of determination we are going to discuss. I think in statistics when you study the standard deviation, standard variance, that time also some book and papers also explain the coefficient of determination, somewhere aligning with the argument we are floating. The coefficient of determination is the portion of the total variation in the dependent variable that is explained by variation in the independent variable, okay, which is explained by the variation independent variable to the dependent variable is basically called coefficient of determination. This measure was originally coined by a geneticist as genesis, the name of the genesis is Sewell Wright in 1921. It is also denoted by R square. Okay. So, small r square if it is a simple linear regression, we already clarified, but if it is a multiple linear regression, that is denoted by capital R square. Okay. That is the difference between small r square, and this is one of the quiz question, and every time it is important. Okay. So, do not get confused, these are the same answer, but this is r small r square is written in case of simple, and that is capital R square in case of multiple regression analysis or model. Now, a diagrammatic Venn diagram explanation for the R square value, that is the goodness of fit we are or the coefficient of determination we are trying to explain, that in diagram A, B and C. Now, you can easily perceive one important interpretation that diagram A as if two variable, that is dependent y and independent x variable, as if there is no relationship. Okay. And whereas in case of C, there is 100% relationship. So, that means where the best fit we derive, it is in the C model, that is equal to 1. Okay. If you wanted to understand the coefficient of determination or the best fit of goodness of fit, C is the best one, the number will be 1. Whereas in case of B model, it varies from 0 to 1. In the first case it is 0, A case it is 0, C it is 1. So, B stands in between. Now, this is what we are explaining in this slide, R square equal to 0 in case of figure A, R square equal to 1 in case of figure C. So, R square lies between 0 and 1 in case of figure B. Then what is the R square in total in terms of equation? This is simply ESS and TSS we already explained sum of square divided by total sum of square. How much the explained sum of square is addressed out of the total sum of square. Total sum of square basically the particular data point as compared to its population parameter, the standard not population parameter, the data point with respect to the average of that population parameter. Okay, that's only counting the total sum of square. Okay, total sum of square when the deviation is calculated with have to the data point with respect to the data point and the average of that data point, then that is called total sum of square. Out of that I already explained that it composed of residual sum of square, okay, and estimated sum of square, explained sum of square. So, not estimated sum of square, it is called explained sum of square. So, the explained sum of square is okay. So, in that case we are actually estimating the explained part through what through the trend line, then that of the trend line is the point for us minus the average of that dependent variable. Okay, that we have already explained. So, what do you mean by R square can also be interpreted when we say it is ESS upon TSS, okay, and TSS is equal to, this is TSS, TSS we have already explained, this is RSS plus ESS. So, so then the next equation follows that 1 minus RSS will actually explain the same R square, okay. Now, the residual sum of square it is I mean you can explain through RSS or you can also explain through ESS, okay. So, R square therefore lies between 0 and 1. So, the closer it is to 1, that means your the model is fit, closer it is 0 it is the worst fit, okay. So, that means that your model is not correct. Okay. The disadvantage attached to this R square measure is that it is an increasing function of the number of regressors. Okay. So, number of regressors if it is increasing, that means if you have more regressor, more explanation will be there to your model, and so R square value is expected to be higher. Okay. So, so R square if it is higher, more regressors are usually in the cross sectional data. We have more regressors. If it is less regressor, then R square value you will get very less. Okay. Now, to avoid this problem, another measure is used to assess the goodness of fit when the number of regressor increases. Now, that defines a better fit to the model, but there are some disadvantages also, like we are not attaching our degree of freedom actually reduces when you have more number of regressors, because the number of parameter also increases. Okay. When the number of parameter to be estimated increasing, so because and accordingly the degrees of freedom reduces, our estimate is going to be problematic. So, therefore, instead of R square, adjusted R square is very important for the interpretation. Not R square is not the right explanation when you have more regressors. Okay. So, adjusted R square take into account number of regressors included in the model. Okay. So, basically we are explaining more than one or more regressors in the model. So, this is denoted by R square bar. Okay. So, make it very clear that whenever R square bar is written, that means we are referring to adjusted R square. In Stata also this notation is going to be very useful. Okay. And I will suggest that whenever you calculate estimate any result, please refer to R square and try to interpret the R square bar. Okay. R square bar. So, how to compute that, that is basically adjusted with, now this is perfectly fine, only we are attaching one important explanation, but what is this 1 minus R square, also important to it, we are taking the ratio of the degrees of freedom, n minus 1 divided by n minus k, k is the number of parameter to be estimated. If you take the ratio like this, we are actually referring to what? We are actually referring to the adjusted R square. Now, the word adjusted here means adjusted for the degrees of freedom, which depends on the number of regressor, that is k. So, if k is greater than 1, if k is greater than 1, obviously your number of parameter increases, and that is in the denominator, and that is in the denominator. So, the R square bar value is going to be lesser than that of the R square. Okay. So, that is less than this. The number of regressor in the model increases, the R square bar becomes increasingly smaller than that of R square. So, the R square is always positive. Now, this is very important. So, R square that is the coefficient of determination is going to be positive always, but R square bar adjusted R square can be also negative, because of the case that we are dividing the degrees of freedom also. Okay. And also there are some negative portion. So, when that exceeds then that of the 1, it could be also negative, but in the rarest cases where we will experience negative coefficient. Okay. Further details we can explore during our experimentation with data. Now, R square bar often used to compare two models that have the same dependent variable. Okay. Now, coming to the standard error of the estimates. Besides that, this is also important for our models. Every coefficient is attached with a standard error, okay, and where the interpretation is very important. Betas are random variables, as their values vary from sample to sample. In statistics, the variability of a random variable is measured by its variance, that is sigma square, okay, and its square root of that is basically square root of the standard basically called standard deviation. So, in regression analysis, the standard deviation of an estimator is actually called the standard error. Okay. So, this is also a quiz question most often asked. I should suggest you to emphasize and read further. The linear regression model, an estimate of the variance in this model, the estimate of the variance of the error term, that is epsilon, is sigma square, which is computed as sigma square hat, then because we are estimating it. So, sum of sigma square, the error square divided by the number of that is the degree of freedom is adjusted with the sample size, the cases n minus k, that is basically residual sum of square divided by the degrees of freedom. If you do it, we are getting the standard error, okay, the estimate of the error term in this model. So, try to remember that RSS divided by the degrees of freedom is the answer for standard error. So, standard error, but that is standard variance. If you take the square root of it, that is basically called standard error. Okay. Standard deviation of the standard variance is called standard error. Okay. This is the equation we wanted to estimate. Okay. So, error, if you remember RSS, if you remember the deviation from the trend line to that of the actual data point, okay, if that is estimated and we divide it by not just n, if you just divide n, that will be not by a unbiased estimator. You have to adjust it, we have to adjust with the n minus k, the degrees of freedom to it, then only it will be estimating correctly. Okay. I think that we have mentioned, this is what I was trying to say. Now, some explanation to be made at this moment to clarify the hypothesis testing, because hypothesis testing requires null hypothesis to be accepted or rejected. Okay. So, usually in our explanation we have to reject the null hypothesis, because null hypothesis usually considered to be the ideal condition, and ideal condition, if it is there, then if it is proved, then there is no actually testing made. So, null hypothesis has to be rejected and the alternative hypothesis has to be proved. So, some significance level, I think you might have heard in different papers that how it is interpreted, we are going to discuss in a short while. So, t test largely if it is k is n is less than 30, but usually what happens our regression analysis, our estimator reduce the estimator to every k at every n less than 30. So, t test in maximum cases is applied because it is applied in cases small sample cases. If we want to test the hypothesis that the regression coefficient, that is beta k, is equal to 0 in case of null hypothesis context, we use t test. Okay. T test usually applied in case of small sample cases, and this t test has n minus k degrees of freedom. And how t is determined? Likewise, z distribution, t distribution, that is estimated value of beta divided by standard area or the standard standard deviation of the standard or of the variance term or the RSS term. Okay. Residual sum of square of the estimator, that is beta k. Okay. So, likewise z distribution, I think if you remember standard z, it is always t distribution is also following the same pattern, only every time we are dividing by its standard error or standard deviation. Okay. So, it is basically the standard error is divided. So, this t value has n minus k degrees of freedom. So, n is the number of observation and k is the number of parameters to be estimated. So, every time k we are referring to the number of parameters to be estimated. In case of sample, do not get confused that in case of sample estimation we talk about as statistics, not the parameter. Okay. The t value t table gives the probability of obtaining such a t value or greater. T table, we have a t table in every statistics book, or even in Google search you will get a standard t values. Standard t tables are there at every degrees of freedom. Okay. You can compare your estimation with that of the standard table at certain level of degrees of freedom. Based on our comparison, I think those clarification we should get it from your statistics and econometrics books. We are only giving you some basic guidance, okay, and then we will quickly start applying the Stata module. If the probability of obtaining such a value is small, say 5% or less, we can reject the null hypothesis. That is beta k null hypothesis, in this case the estimated value of that beta coefficient of the relationship between these is 0, basically there is no relationship. Okay. If I am saying beta k is 0, basically x and y having no relationship. Usually in the ideal condition there is no such relationship. We have to prove that yes, there exists a relationship, and with our significance level we can able to prove that your null hypothesis is rejected, your alternative, that is it has a relationship, alternative hypothesis is validated. Okay. What I wanted to mention that if it is 5% or even less, we can reject the null hypothesis. It means that the estimated t value is statistically significant, okay, and significantly different than that of 0. So, some common standard limit of rejection or acceptance, any way you can interpret. The common probability values, those are defined, and accepted is 10%, that those are 10%, 5% and 1% level. So, alpha values, these are also called type 1 error, alpha values to define the significance, and these are also called level of significance. One important clarification I wanted to mention that usually that means 10% error or 5% error or 1% error is acceptable, okay, in any model. So, then now if it is exceeding 10% error, then we will certainly say that your model is not a best fit or is not a good model, your coefficient is not estimating correctly. It is not proving your hypothesis. Now, so basically any point you can also test your model. The level of significance could be like here it is 0.10, here it is 0.05, here it is 0.01, okay, at 1% level. But now there are some cutoff points for better interpretation. That does not mean any other value is not important. You can also test at 0.06, you can test also at 0.02, okay, or any level till 0.10, that is 10% level you can test, okay. So, there is no hardship, but it is little complicated because those standard values are difficult to derive, okay. So, Stata provides t value along with its p values as well. So, that is the important aspects in Stata we are going to refer in our next class. A low p value the probability limit value suggests that the estimated coefficient have significant impact on the regression. Okay. So, low p value we are going to define in our interpretation. Similarly, we are also supposed to compare with the confidence interval. So, confidence interval actually defines the distribution of the data. Okay. So, accordingly we can, once the interval is defined, what are the extreme limit, the alpha limits are there, and so that we can able to take a decision in terms of the significance level. So, Stata also computes a 95% confidence interval for individual regression coefficient. It provides a range of values that has a 95% chance of including the true population value. Okay. So, we will interpret those with the help of data. This 95% is called the confidence interval computed at 100 that is that is 1 minus alpha. Okay, at 100 level, that is 1 minus alpha. If 95% basically means 5% error, we are going to estimate. So, it is 1 minus alpha means 1 minus 0.95, that is 0.05. Okay. So, 1 minus alpha is a confidence interval for population coefficient is calculated as, that is the probability limit. How you can get it, the details from the statistics books, that it actually defines as, if it is a two-tailed test, something we also discussed from the beginning of our lectures. If it is a two-tailed test, then the probability limit with its standard error that is defined with beta k plus minus t value alpha alpha divided by 2 we refer to, if alpha percentage we know that at 5% level or even 10% level. If it is 5% level, then t value we need to compare with 0. Instead of 0.05 we are comparing at 0.025. Okay. So, we need to divide into two categories with its standard error, that with a probability limit that will define our confidence interval, that is 1 minus alpha. So, t alpha by 2 is nothing but the t statistics obtained from the t distribution from the table. Okay. But be careful that what is this which tail test, usually it is two tail test we refer, because the data may be distributed from from in a normal shape. So, there are possibility of both sides, is not it. So, alpha by 2 is nothing but the level of significance, maybe 5%, maybe 1% with appropriate degrees of freedom. Standard error is noted with AC of Vk, and so if that limit is lower the limit, and because okay, basically when you subtract the beta value to its the tabulated value with its alpha significance level with their standard error minus, if you are subtracting it, you will get the lower limit of the confidence interval, lower limit is compared to upper limit. We will explain with the help of data also. If you plus it from the mean value to its deviation explained by the error term, that will define the upper limit of the confidence interval. We will explain this later. Similarly, the F test is also used to understand the significance of the slope coefficients. Like F test is used to test the significance of all the coefficients simultaneously. Okay. It is also known as overall significance of the regression. The formula for is in that case we said RSS was important. Now we are saying RSS with its standard error we define in case of t, but now we are comparing the exponent sum of square as compared to with residual sum of square, and their respective degrees of freedom are also divided. If the computed f value is greater than critical or benchmark f value at the chosen level of alpha, we reject the null hypothesis. It means that at least the one regression is statistically significant. We are going to discuss these details in due course of our time. I know that these are simply formula, unless we do not test it with the help of the real life data, it might be difficult for you for your better interpretation. Our purpose is to explain through Stata. So, this lecture so far gave you a clear background of what are the basic test, basic necessary steps we must follow and we have already guided. With this, I think I should not stress further. We will continue and carry forward our Stata application of the OLS in the next class. For at least for half an hour we will spend on understanding the applications. Okay. So, thank you very much.